and just in general. It's good to be present, you know? Namaste. So, vibration isolation table analysis. In this example, we exercise many of the methods for modeling and analysis explored thus far. So we're going to bring them all together. We're going to use this physical system here. We're going to create several different models for it and do some analysis on it. So it's a vibration isolation table, which tend to be these tables with big mass. I guess like typically just the tabletop's very massive, like made from like concrete or something, like really heavy. And then it's got legs some of the time at least, or frequently at least. The legs have some sort of like rubber element in there in line so that you have to transmit any vibration from the floor through that element, and it damps some of that out. The idea is you're trying to isolate whatever's sitting on top of the table from whatever vibrations are coming from the floor, especially if it's in an environment that is noisy, like a shop or industrial environment. Some instruments will break if you subject them to very many vibrations over very much time. So the floor is moving. Did anybody read the old Hardy Boys books growing up, the old ones? Do you guys remember that one where like the guy, like they find this guy and he's like his skull is like cracked open and like he like before he dies he's like the floor, and then and then they discover after a long time that like the floor of his bedroom, he didn't know this, but it like went down to the basement or something, like it like lowered down to the basement, but all the furniture was bolted to the walls. So I think he like got out of bed in the night or something like that, and it had gone down, and he like fell all the way, and then the floor came back up, and it was like, ooh, how did he fall that far? And anyways, that's what they discovered. So the floor is moving is the reference. Did anybody read that one? Yes. Oh man, I really like the one with the fireplace, the false fireplace. Oh my God, there were some really good ones. I missed those books. I read a lot of those books. So given the vibration isolation table shown, it's vibrating, the floor is moving, so Vs is the velocity source input, going through a spring and a damper. I give the mass, spring, and damping coefficient, so I give those actual values. And we're going to come up with a linear graph model, a state space model, skipping this for a moment, a transfer function model, and then put up a differential equation model. So 4 different system model representations. And I think that's all that we've learned about. I think that's all we've got. Yeah. There's only one more that we learn about in system dynamics. So you've learned like a lot of the different representations already. So we're going to come up with all these different models for it. And we're going to also find the equilibrium state for unit step input, and we're going to find the system stability, and we're going to solve the differential equation using a little of the old superposition and a little of the old differential property of LTI systems. So that's our goal today. And I gave you like all the fill-ins because there was just too much to cover in one day if I wrote everything. So I gave you most of it, or actually all of it, except for the brackets don't come in ever. And it really is annoying in this lecture because there's a lot of matrices. So, barf. Okay. So the first step we're going to do is we're going to find the linear graph and state space models, because that's like wheelhouse now, right? Like we're getting comfortable with that. So 3 nodes, one of them's ground. Velocity source goes into one massless node, goes through spring and a damper in parallel to the other node, which is a mass node. And that connects to ground, of course. So the normal tree is drawn on here in green. Looks better on that screen. And this means, so from the normal tree, we can tell that the velocity of the mass is a state variable and the force through the spring is a state variable. So we can write our input, state, and output vectors, I decided that the output was going to be the velocity of the mass. That's what we care most about. That's what the vibration of the device that is sitting on it is going to see, right? Is the velocity of the top of the table. So, the heavy top of the table. So the elemental equations are as follows. I'm going to use dot notation because we don't have any circuits going on in this problem, so no I to worry about. So Vm dot equals 1 over m Fm, Fk dot equals kvk, Fb equals bvb. The usual elemental equations for a mass, a spring, and a damper. The continuity equations are those that need to be written for each of the passive branches of the normal tree. So there's only one. It needs to be cut once by a contour. So it's leaving the node. The force on the mass is leaving the node, so it's equal to everything going into the node. So Fk plus Fb. There's that. Compatibility equations, we need one for each link, right? So one for K, one for B. And they both connect across the same terminals, so they both equal the same thing, which is Vs minus Vm. So bam, bam. It's almost like, I want to say meditative now, right? We go through this process, it's like the same steps, we know the steps, they come to us, they stay for a moment, and then they leave. Namaste. Okay, so the state equation can be found by substituting the continuity and compatibility equations into the elemental equations. So, usual thing. These guys up here. And then we just need to eliminate FB. So, FB is going to show up in this one for FM. So, we're going to have to plug that in there. And we're going to be down to two equations. Write it in standard form, which looks like ass. But is this? Yeah. So this is, a good old-fashioned state equation. Oh, by the way, several folks struggled with two different things on the output equation. It's always the output equation people struggle with, which is the easy one. If you have two outputs, you need two rows. You have three outputs, you need three rows. The number of outputs equals the number of rows in these arrays. So there was some confusion on that. Also, this is not y. This is x. So don't put y there. Y is what you're writing the equation for. So don't put y in there for your x. I saw several people do that. I mean, I know you got people in the test pressure and all that, but just pointing out common errors from the exam. The exam. I'm not handing out till the end, you guys won't pay attention to me. But I'm going to dangle it. It's the carrot at the end. Okay, so congratulations. Many of you did very well. We are going to also look at the equilibrium, right? That was one of the questions that was asked, is what's the equilibrium state when you have a velocity source input of 1 meter per second, constant. So that lecture, I believe it was lecture 5.1, says that there is one equilibrium state if the A matrix is invertible. And so we determine if it's invertible by just trying to take the inverse and seeing if anything goes wrong. And nothing goes wrong. But I want to mention, so I switched the order of where this inverse thing happened. So, or where this part happened. So I ended up having this footnote showed up on the second inverse that I took instead of the first inverse. But if you look, it's pretty good. It's a pretty good appendix in the Rowland Wormley text. A43 talks about how to take the matrix inverse by hand. For smaller matrices, we want to be able to do that. So I want you guys to be able to, by hand, be able to do a 1 by 1, which is just the reciprocal. So now you guys can do that. A 2 by 2, which is this case. And then I want you guys to be able to do a 3 by 3. If somebody on Slack reminds me, I will post a good formula for it, so you guys can just plug and chug if you want. Because I know that you guys don't have linear algebra until next semester. Well, some of you don't. Some of you do. Okay, so here we go. For a 2 by 2, the nice way of doing this is so that it's the adjoint matrix divided by the determinant of the matrix. That's the matrix inverse. And for small matrices, it's easy enough to compute that. So the adjoint for a 2 by 2 is actually very simple. You just take the original array and you swap the two diagonal terms. So the 0 went up to the upper left, and the negative b over m went to the bottom right. So you swap the diagonals, and then the other two you leave where they are, but you just change the sign on them. So instead of 1 over m, we have negative 1 over m. Instead of negative k, we have k. So that's how you do it. That's the adjoint. And then you divide it by the determinant of the original matrix. So the determinant of a 2 by 2 matrix is very easy to compute. It's this term times this term, so the diagonal terms multiplied. Then you subtract the product of the off-diagonal term. So it's this term times this term minus this term times that term. So it's plus minus. Okay, so it's negative b over m times 0, which is 0, minus 1 over m times negative k, which is negative times the negative positive k over m, 1 over k over m. So this is the determinant is 1 over k, 1 over the determinant. This term is 1 over the determinant, and so 1 over k over m. So there's our inverse. And notice that nothing bad happened, so it exists. Actually, something bad could happen. If k was equal to 0, something bad would happen. And so we fortunately know k, and it's not equal to 0. So we're good. Awesome. So it has an inverse after all. Let's use this to compute the equilibrium state. Back in lecture 5.1, it was 5.2 that we did this. We learned how to find the equilibrium state for a constant input, u. And so this is the formula. We have the inverse already. We just found the inverse. And so I'm just going to plug in. So our inverse, I plug that in. Negative sign came from this negative sign. And then the B matrix, and then the input matrix is just U. It's 1. So that has no impact. The 1, it's the 1 by 1 identity matrix. It's just 1. So nothing happens to that one. This term is the product of these two matrices. So 0 times b over m plus negative 1 over m times k gives us negative k over m. K times b over m minus b over m times k, which they cancel conveniently to 0. The last step is to distribute this scalar in to each element of the array, of the matrix, and so that is easy enough. And wow, everything cancels except for a 1 and a 0 that remain. So the equilibrium state for an input velocity of 1 meter per second at the base is to have the tabletop going at 1 meter per second also, and having no force transmitted through the spring. So that's a pretty, I think, intuitive equilibrium. We would expect that to be an equilibrium, right? Like where it's not transmitting any force and the velocities are the same. They're moving together at one speed. So the system is in equilibrium with that state. Since Vm is also our output, so remember that is the output that we're solving for too when we finally do that solution. We expect that it will be in equilibrium in steady state, of course, right? So that we expect that 1 meter per second to be our steady state output value. We haven't computed the output value for all time yet. We just computed it like the steady state final value. So it should go to 1 meter per second. That's a good way to check our solution that we're going to develop in the coming parts. Okay, transfer function model. transfer function h is going to be Vm over Vs. And I should have put the input-output differential equation, I say, with input Vs and output Vm. A transfer function model, technically, it isn't, you don't actually need to write with input Vs and output Vm because you can just find the matrix transfer function, right? But we only have one input and one output, so you end up just with exactly the transfer function that we would have if we knew it was Vs and Vm, but in any case, not that big of a deal either way. So h, our transfer function, we know it's going to be scalar because we only have one input and one output, so it can only be one transfer function. So it was going to be used as a bridge to our input-output differential equation, right? That's why we defined the transfer function before. We'll learn a lot more about the transfer function later. So it's defined, or you can find it from the formula, which we saw a few lectures ago. So all you need to know are the A, B, C, D matrices, and we have those. So we just have to plug and chug, right? So let's first compute. So the most difficult part of this is always computing this inverse. So let's do that separately. So SI minus A inverse looks like this. So the identity matrix, the 2x2 identity matrix looks like this. S times that, so you can just multiply S through S, 0, 0, so that's what this is, SI. The identity matrix takes whatever size the A matrix has, so it's a 2x2, so the identity matrix is a 2x2. And we subtract out A matrix. So we can do that first. Whenever you do addition or subtraction with matrices, it's just element-wise, right? So we do the addition and subtraction. So we're going to subtract each element of A from each element of SI. So S minus negative B over M is S plus B over M. 0 minus 1 over M is negative 1 over M. 0 minus negative K is K, and S minus 0 is S. Feel like often when we take 0 minus something, people forget about the negative sign. It just happens a lot. Just something to keep in your mind. Don't forget the negative sign. Okay. Good. So we take this inverse. Once again, we can use that formula, the adjoint one. So we flip-flop these two. So S goes to here. S plus B over M goes to there. Switch the signs on these two guys, and we're ready to roll. All we need to do is find the determinant of this original matrix. So it's S plus B over M times S, that's this first term, minus negative 1 over M times K, which is the second term. So same process, same formula. And in the appendix that I refer you to in Rowell and Wormley text, it has a formula worked out for a general 2x2 matrix. And if you remind me on Slack, I'll give you guys a general formula for a 3x3. So just plug in. I mean, you don't have to. Everybody can just plug into things. I mean, it doesn't give you a deep understanding of the matrix inverse, but hey, it's okay for now. You guys will learn that in your linear algebra class. So the last step here is to simplify the expression. So simplify this determinant, which looks like that. Okay, so now we're ready to compute the entirety of H. So we're just going to plug in to this formula. So we just got this. So now we're going to plug in C, B, and D, right? Which is now legal in Washington State. So that was I'm not sure. I thought it might be too obscure for anyone, but a couple of you chuckled. I know who you are now. It was a trap. Okay, so here's our C. Here is our B, and here's our D. This is SI minus A inverse. This is part of it too, right? I pulled that term out. This is the 1 over the determinant term. I pulled it out. It's a scalar, so when you do matrix multiplication and you have a scalar in there, you can always pull it out. So I do that. And then, so C times this matrix times B. As you guys may or may not be aware, if you have 3 matrices, I'm going to call them X, Y, and Z. You can multiply the first 2 together first and then multiply Z second, or you can multiply Y and Z first and then multiply X. That's fine. So you can do it in any order in that sense. However, you cannot switch the orientation of these. So you cannot, so for instance, X, Y is not in general equal to Y, X. So you can't just flip them in that sense. You can compute the products in any order, but you can't switch the order of the matrices. So this is, so we can take C times this matrix first, or we can take this matrix times B. I'm going to go with C times this matrix first because multiplying something by 1 and a 0, super easy. Multiplying it by B over M and K, nah, not as easy. So I'd do that. 1 times S plus 0 times K gives me S. 1 times 1 over M plus 0 times S plus B over M gives me 1 over M. Still have this B. The D matrix is just 0, so that goes away. And then finally, we have one more matrix product to take. It's a 1 by 2 and a 2 by 1, so we'll just have a scalar remaining at 1 by 1. And S times B over M, and then 1 over M times K. And that's the numerator of this term here. So we have our transfer function. Hooray! From that, we can derive the input-output differential equation from the reverse procedure from lecture 3.7. And in lecture 3.7, what we did is we took the Laplace transform of the input-output differential equation, and we derived the transfer function from it. In this little bit here, we're going to go from the transfer function to the differential equation, which is essentially the same exact procedure, but we take the inverse Laplace transform. But really, it's just like by inspection, because we don't really get into the details of the inverse Laplace transform, because all we care about is the derivative term Laplace transform, which is always just s to whatever power is the derivative to that power, that order of derivative. So we have our transfer function is Vm over Vs. Laplace transforms of them, right, is equal to this. We can, as we like to say, cross-multiply, right? Multiply both sides by Vs, multiply both sides by this s squared plus b over ms plus k over m. And then we have this expression, 512b. Now 512b is starting to shape up, starting to look a little bit like the differential equation. And we can distribute the Vm if we wanted to each term and distribute the Vs. Or, as we're going to do, we can recognize that there's going to be a Vm in each term and say, oh, s squared Vm, that's going to be, in the time domain, the inverse Laplace transform of that would be Vm double dot, the second time derivative of Vm. The second term, b over ms, is going to be, so the b over m is just a constant, it stays out there. The s, if you took s Vm and took the inverse Laplace transform, you would get Vm dot. we went the other way before, right? VM double dot, we went to S squared VM. Now we're going the other way, but it's the same. K over M times VM, and there's no dots because there are no S's. On the right-hand side, B over MS gives us a VS dot, and then we have K over M VS, and there's no dot because there's no S. So this, my friends, is our input-output differential equation. We've got it. Easy peasy. Now, we do have a derivative of an input, which looks kind of scary. But even if we have, so we could just take the derivative of the input and stick it in there and go forth and try to prosper. But we're going to use superposition. So, and the derivative property of LTI systems. So the step response is found using superposition and the derivative property. The forcing function, which is the whole right-hand side, right? The whole right-hand side is the forcing function, f of t, is equal to this. It's composed of two terms, one of which has a derivative of the input. Rather than attempting to solve the entire problem at once, which we could do, we choose to find the response for a forcing function just equal to 1 first. So the Vs is actually 1 in our problem. But we know that if we know the response to just 1 being the forcing function, then we can actually combine solutions using superposition with the adding and the multiplying, and the derivative property, which is the derivative term. So instead of having to do a bunch of work, we can do less work, which I'm always a proponent of. I mean, it depends. For me, not necessarily for you. You guys need to do a lot of work. So, yeah. So that's generally the plan. Is like we're gonna set the whole side, instead of being all this crap, we're gonna say, oh, f of t, that's just 1 for now, and then we're gonna say, oh, if we scale that 1 by k over m, and we take the derivative of it and scale it by b over m, that's the solution for that whole forcing function. So that is our plan. So first we need to find the unit step response, and we follow the same procedure as usual. The characteristic equation is a polynomial in lambda, right? Boom. Do you guys notice something here? I mean, we aren't gonna like belabor this point, but this characteristic polynomial is just like something over here. What is it? It's the determinant of Si minus A. Except for instead of S's, we have lambdas. Suspicious. Turns out that's always true. And that you can find out all kinds of stuff by looking at the determinant of Si minus A. And for those of you who are, keeping score at home, these are the eigenvalues. Yeah. But we don't need to talk about that yet. We haven't talked about eigenvalues yet, but they are the eigenvalues. We will get there. For now, they're just the roots of the characteristic equation when we're trying to solve this input-output ODE, right? So we do the solution. Little quadratic formula gives us this. We plug in the numbers at this point. Why do we do that? We need to know if it's a real, if there are two real solutions, if they're repeated root, that could be possible. If it's complex, imaginary, what it is, and it turns out to be complex. And we could just use these numbers in the rest of the solution. However, I found it very tedious to keep rewriting these numbers. So, and also, we want to be able to do it for any numbers that happen to be the complex roots of our characteristic equation. So I just say, I'm going to call the real part sigma, and I'm going to call the imaginary part omega, the positive imaginary part omega. so that we have sigma 1 or lambda 1, 2 equals sigma plus or minus j omega. That means the homogeneous solution, as always, except for when you have a repeated root, is C1 e to the lambda 1 t plus C2 e to the lambda 2 t. In this form, however, C1 and C2 are complex numbers. That's a bummer. I don't really like that. I mean, like, yes, you could do that, but I felt like we would be more comfortable transforming this into something that probably looks familiar to you. You probably used this later formula that we're going to derive in your differential equations class. That's my guess. So instead of using this form, we're going to transform this. So if we plug in lambda 1 and lambda 2 in terms of sigma and j omega, sigma and omega, we get this expression. There's a common factor of e to the sigma t in both terms, right? E to the sigma t, e to the sigma t. We can pull that out. So that's what we do, factor it out. And then we apply Euler's identity. So Euler to both terms. So e to the j omega t and e to the j omega t separately. We apply it, and we get this. So this is all from the first term, and this is all from the second term. It's kind of getting a little ugly, but we're going to combine the cosine and sine terms here, and we get this expression. Okay? So a little bit better looking. And then we're going to do something surprising. We're going to say, okay, I'm going to call this a new constant, C3. And I'm going to call this a new constant, C4. No reason not to. They're both constants. They're complex. C1 and C2 are complex. Turns out that C3 and C4 are real, which is convenient. And you get this form here. VMH equals this. Now, this is probably the one you guys used in your differential equations class. But I don't know if you guys saw the derivation of it, but it's good to do that. We are going to stop doing this derivation now, though. We're never going to do that again. We're just like, we did it that one time, but when you guys are solving this, I would not recommend going through this derivation every time because that takes time. So I would skip. You would say, oh, lambda 1 and lambda 2 are complex. I would skip right down to this guy. And then next term, we're going to learn about how to find a bunch of solutions like this in the book. Chapter 9 of the textbook has a lot of these solutions. This is one of them. This is a decaying because sigma is less than 0. So it's decaying because sigma is negative, right? So this is an e to the minus t that's tuning everything down as time goes on, right? It's dampening everything out. And then this is a sinusoid. So it's a decaying sinusoid. A nice aspect of this new form is that C3 and C4 are real. Now the particular solution could be found. So we have a homogeneous solution. Done. We have the undetermined constants here, C3 and C4, that come from the initial conditions, right? We haven't applied that yet. Now the particular solution can be found by assuming a solution of the form of the constant, because we have a constant input, so we expect that there's a solution that is a constant. So an undetermined constant, or coefficient, so substituting it into the original differential equation, but we set the forcing function equal to 1, importantly. We set it equal to 1. And that's because we're only solving the differential equation right now for the forcing function equal to 1. If you didn't, you would have to include the other terms, which is not what it's about. You don't want to do that. So we attempt to find the solution for k, and it's easy enough solving this equation for k. I think we could all do that because the time derivative terms of a constant go to 0. So yeah, that is our solution for k. So it is a solution, and therefore the general solution is the sum of these two, the homogeneous solution that we have, the particular solution that we just found, and we get 518b. So this is the general solution, right? I'm saying VM step because I'm saying, okay, our forcing function right now is just step, just unit step. We're going to have to use superposition to find the full function. And then general solution, you typically applying the initial conditions is one of the relatively easy parts. But in this case, it's a little tougher because you have to take the time derivative of this function, and this is a product rule situation, so you get kind of a mess. Because there's two initial conditions, right? Because it's a second order system, you need two initial conditions. We're not given in the problem, so VM of 0 is not given, and VM dot of 0 is not given. So we, as is typically the case, if we're not given initial conditions and we want to know the response of the system to some input, we say the initial conditions are 0, okay? So we need to apply initial conditions VM of 0 equals 0, and VM dot of 0 equals 0. So we need to know what VM dot is if we're going to find what VM dot of 0 is. So we compute that, and that's 519. This is the part I screwed up on, actually, as I was doing it last night at 2 a.m. And that one just like really kept me up for a while. I was like, I surely can do this in my head, typing it directly into LaTeX and not write this on a piece of scratch paper. Wrong! I cannot. So now, applying the initial conditions, VM of 0 equals 0, and VM of 0 equals 0 again, we have C3 and C4 solved for. So in terms of parameters that we know, so it's good form to rewrite it as a single sinusoid. So we have currently, the current solution is in two sinusoids, right? Cosine and sine, with no phase, so you know you can combine them into a single sinusoid. So this is that single sinusoid. You could have chosen cosine or sine. The formula that we're using here, the formulas are found in this section A211, so it's the appendix of these notes. So, is it 11? I was thinking it was 14. It's 14, isn't it? I don't know why it says 11. Sketch. Don't trust 11. 14? Question mark? Okay. Okay, so we use that formula, which pretty much says here if you have A sine U plus B cosine U, you can combine this into this single sine or cosine A squared plus B squared times, I think if it's a sine, it's sine omega t plus arctangent of A over B. I don't remember. I don't know. Look it up. Don't trust that formula. That was off the top of my head. We know that I am flawed. But I have flawless hair and style. Okay. So 522a says that the amplitude, the single amplitude for the cosine, so I went with cosine. I could have chosen sine. I chose cosine arbitrarily. And these are our A1 and Psi1. So A1 is that, Psi1 is that. Combine it into a single one. So we see very explicitly this is a sinusoid with some phase off from the input phase. It decays to some steady state value. So that's our step response. So now we're ready. We have our response to a forcing function of a step input. We want to know what the response is for a forcing function that is a linear combination of the input and its time derivative, which is to say the forcing function that we actually have back here, this guy. That's the one we want. We want the response to that. We just found the response to f of t equals 1, which is like fine, okay. But now we want to know what it is for f of t equals this. Well, since Vs is 1, we have just a linear combination of the input, and with a time derivative in there. And so from superposition, if you have a linear combination of an input, if you know the response of that input, you can just take the linear combination of that to find the output. And take that in combination with a derivative of an input that you already know the response to is just the derivative of that response. So yeah, it's pretty nice. So we're going to use that. It's expedient to rewrite the time derivative of the unit step response. So we're going to do it using the final form that we had here, which has gotten kind of assaulted by all of this notation around it. So I'll delete all that. But this is the VM step that we're taking the time derivative of, and it's equal to this, where I combine it. So after I take the time derivative, it splits me into two signs again. Or two trig functions again, which sucks. So I'm going to recombine them. Because they have the same argument, right? The cosine and the sine terms have the same argument, so I can combine them using the same formula. I get a new phase addition, and I get a new amplitude addition. And so I define what they are here. So I just use the formula again twice. I use the cosine one again for consistency? I don't know. This is arbitrary again. I just chose to do it again. Finally, applying superposition and the derivative rule of LTI systems. So now we're ready to go. So now we have, so our solution for our VM was found in 521b, right? So we know this from 521b. And now we know what VM step dot is, which is 523b. 523b. Now, all we need to do is plug it in and take the linear combination of them. So b over m times this, k over m times that is the solution. Is our solution by superposition and the derivative rule. And that is just this.
Where did plus 1 come from?
Yeah, it came from this guy. So it was plus m over k, and we multiplied that by k over m. So we distributed the k over m. The first term picked up a k over m. The second term canceled k and m conveniently. And actually, before we even look at the plot, this term goes away because we have e to the minus something t, right? Right there. This term goes away because we have e to the minus some term, e to the minus something t there, too. So all we're left with is 1. So what is the steady state? 1. Which we said it needed to be because the equilibrium, when you have a constant 1 meter per second input, is 1 meter per second output. So that's good. Let's go for consistent. This is how I was debugging my stuff last night. I was like, so this can't be right. I'm not getting 1 out. So yeah. So this is the solution. It's worth plotting the results. So I do it in MATLAB, just give you guys a little bit more exposure to plotting stuff. So define the constants, define the secondary parameters. So I'm just using the formulas that we derived before. Define sigma, define omega, A1, A2, psi1, psi2. Using this atan2 function, which is nice. It keeps track of which quadrant you're in because arctan by itself does not. So That's a nice little fun. Every programming language has its own ATAN2, and it often is with a 2 on it, and it's a 2 argument function. So you give it the numerator and then the denominator in MATLAB. In Mathematica, it's exactly the opposite. It's the denominator and the numerator, because nothing makes sense and we're all going to die. Okay, so finally the solution for Vm of t can be defined as an anonymous function. So now we've got our solution. So I just literally typed in the solution that I had. Well, no, I typed in the solution that I had that was incorrect first, and I ran it, and I was like, nope, that's not it. And then I finally corrected it. So I don't want to give the impression that this just all like falls out beautifully for me every time. It does not. I get confused, and I'm like, what the hell? Do physics work? I don't know. Maybe. Now plot over the first few seconds. And so this is just the plotting stuff, and the spacing is all weird on this sheet for whatever reason. So now know that the steady state output value agrees with the predicted equilibrium analysis above. So bam, we get over 3 seconds, the velocity goes from its initial condition, good, it started out at its initial condition, which is a good thing to check, and it goes up to almost 1.5, and then it oscillates and it damps out to its new steady state, which is 1 meter per second. So this is exactly what you'd expect. If you have this system, it's always good to check this, right? So you have a system where you suddenly input 1 meter per second to this side, the lower side. The upper side is going to go up, and it's got some spring to it. It's going to go up, and it's going to oscillate, but then it's eventually going to die down and move with the input velocity. Okay, the last thing to do was the stability, and we have learned what we need in order to analyze the stability. The roots of the characteristic equation were this, which clearly all have negative real parts. So that was what we needed to test, right, for stability. The real parts of the roots of the characteristic equation, and they're all negative, and therefore the system is asymptotically stable. So that's good. If even one of them had not been negative, had been positive, if even one of them had been positive, it would be unstable. If even one of them had been, if they were all negative except for 1 or 2 or 3 were 0 real parts, it would be marginally stable. And if any of them are positive, it's unstable. So we have stable because they're all negative. All negative real parts. Real part's the part that matters. Obviously, the imaginary part doesn't have to be anything in particular. It's just the real part that matters. Okay, it's been fun. That's all I got for you. Until like a month from now. See you later.